In this problem, we're trying to determine a formula for the volume of a cone, which is inscribed in a sphere. Now, inscribed basically means to have a perfect fit, so the cone is extended as far as it possibly can be within the sphere, so it's making contact with it. What would be wise is to pause here, read the question thoroughly so you get all the details before we start actually trying to solve for the volume. Let's have a look at some of the key words. We need to find the volume of the largest right circular cone, so in other words the cone is pushed right to the boundary of the sphere. It has a semi-vertical angle x and it is inscribed in the sphere, and we're trying to determine a volume formula based on those key details. Now, just for clarity, in this formula we can see that we've got x, that's the semi-vertical angle, so we need to establish where that is. And we've also got r in the formula. Now, r represents the radius of the sphere. Let's have a look at a 3D diagram to get an idea of what we're talking about. So we can see here our cone has actually been placed so that it fits right to the boundary of our sphere. But to put the information in with a vertical angle and radius, what we would prefer to have is a 2D diagram. So we've taken a cross section here. Again, we can see the cone is pointing downwards and the vertical angle will be in the lower part of that cone. Now, in our two-dimensional diagram, we've drawn 3 lines from the centre, and each one of those is equivalent to the radius of the sphere. We'll use those to establish some of the lengths within this diagram. So we've put capital R to refer to the radius of the sphere, and for clarity what we'll do is we'll use small r for the radius of the cone. You can see we've put small r at the top of the diagram because that's representative of where the circular base of the cone would be. And we've put a K from the centre towards the circular part of the cone because the K and the capital R will help us establish the height of the cone. Now, the next step is using our diagram is to place the semi-vertical angle x. You can see that we've shaded where angle x is. It's basically at the apex of our cone facing upwards, but it's not the entire angle, it's only to the vertical, and hence the terminology semi-vertical angle. Now what we'll do is we'll use that to help us determine another angle within the shape. Now we can see we've placed 2x at the centre of our circle, again facing upwards, and the reason why that's 2x is because there is an angle property in circles that says if you have an angle where the vertex is at the circle and it's subtending the same arc as an angle where the vertex is at the centre, the angle at the centre is twice as big as the one on the circle. And admittedly that's for an entire angle facing an arc, but because we've got a vertical line that splits our angles in two, the same property applies. So x, the angle at the circle, will double when the angle's written in at the centre of the circle. Now, to establish some lengths in our diagram, let's label the circle at the centre triangle BCO. This will help us to establish the value of K. So if you look carefully, we do have a vertical meeting the line BC, so there's a right angle there, and we have the angle 2x. Now K is adjacent to the angle 2x, and capital R is the hypotenuse. So we can use cosine, in this case cosine of 2x, to describe the ratio of adjacent over hypotenuse, or K over R. We'll then take that a step further and say that the side K is equal to R multiplied by cosine 2x. Now that'll help us establish the height, in this case the height of the cone. So the height of the cone is K plus R, and because K is equal to R cosine 2x, we can write the height as R plus R cosine 2x. Now let's use the same triangle, BCO, and this time we'll use it to describe the radius of the circular part of the cone, and we've labelled that with small r. Now small r is opposite the angle 2x, and capital R, the radius of the sphere, is still the hypotenuse. So we can describe sine of 2x as opposite over hypotenuse, or in this case small r over capital R. We'll rewrite that expression so that we get the radius of the cone, small r, is equal to capital R multiplied by sine 2x. So that now gives us a description for the radius of the base of the cone in terms of the information we originally had, which is the radius of the sphere, capital R, multiplied by sine 2x. Now let's use the information that we've got on the radius of the cone and also the height to determine the volume. We've got the basic formula to start with, which is the volume is equal to 1/3 the area of the circular region of the cone multiplied by the height, or that's 1/3 pi r squared multiplied by height. Now we have got information based on what we saw before in the diagram. We've got the radius of the cone in terms of capital R and X, and we've also got the height of the cone in terms of capital R and X. Let's substitute those values into the volume formula. So we'll start by substituting in the radius for the cone, which is r sine 2x, and of course that's squared. So we get the volume is 1/3 pi capital R squared sine squared 2x. And then we'll substitute the expression in for height. That's capital R plus R cosine 2x. Now you can see in the expression in green that we can factor out a capital R and bring that towards the front so that that will establish the R cubed for us. So we'll do that first of all. The next step will be to look at the expressions for sine 2x and cosine 2x. In the original formula that we're asked to solve, the angles were expressed just as x, not 2x. So what we'll do is we'll use trig identities. There is one for sine 2x that describes sine 2x as 2 sine x cosine x, and also cosine 2x is 2 cosine squared x minus 1. So we'll substitute those into our formula. So if we do that, the expression in blue then is squared, so we get 2 squared is 4, and then we get sine squared x and cosine squared x. The second part of the expression in green, the 1 minus 1 actually cancel each other out, and we're left with 2 cosine squared x. Now what we need to do is simplify the expression further, because we have got 4 and 2 being multiplied in that expression, and we've also got cosine squared and cosine squared again. If we bring those all together, 4 2's are 8, and that means at the front of our expression we've now expressed 1 multiplied by 4 by 2 as 8. That's on the numerator of the fraction. We've got cosine squared multiplied by cosine squared, and that gives cosine to the power 4. So that expression in black, as you can see here, is the expression that we're asked to solve. So we've determined that the volume of the cone, based on a sphere of radius r, with the cone having a semi-vertical angle x, is 8/3 pi r cubed, r being the radius of the sphere, sine squared x multiplied by cosine to the power 4x.